Okay, so this is the 2023 Higher Level Applied Maths paper, question 3. The photograph on the right is of a chain swing ride in an amusement park. The disc at the top of the ride is rotating in a horizontal plane. People sit in seats which are attached freely by inextensible chains of length 4.3 meters to fixed points on the disc. The chain attaching seat A hangs from point X on the ride and makes an angle alpha with the vertical. X is 3.5 meters from the axis of rotation, which is the vertical line PQ as shown in the diagram below. The chain is free to swing in or out relative to PQ. The ride rotates about PQ with constant angular velocity omega. Seat A moves in a horizontal circular path which is 6 meters above the ground. Okay, so this is our diagram, or the diagram that they give us here. So it's 3.5 meters from the axis of rotation here, PQ. It's rotating around here. This is our chain, this is the seat, and this is the angle alpha here. And the length of our chain here is 4.3 meters. And the seat then is 6 meters from the ground. Okay, so let's see what we have to do first. Draw a diagram to show the external forces acting on seat A. Okay, so we've got to draw a diagram and put in the forces then. Okay, so we have, first of all, we have our chain there, we have our seat A, and there's a tension in the string anyway, or a tension in the chain in this case. The seat itself has a certain weight, and that's going to be force downwards, mg. Now, if we want to resolve the forces, let's see, we would have force coming out along here and force up along here. Our angle is here, so this force along here would be T sine alpha, and that's actually the same as the centripetal force towards the center of rotation, and that's going to be m omega squared times r, that's towards the center. And up along here then we have T cos alpha. So I think that's really all we need to do there. These are the external forces acting on seat A. Okay, so let's go on to the next question then. Show that omega is equal to the square root of g tan A over 3.5 plus 4.3 sine alpha. Now, when you look at this, you can see there's a 3.5 here, and we know that 3.5 is this distance here. So presumably that's going to be the distance from the center of rotation from here all the way out to our seat. So we've got to add this amount here, the distance from here to 3.5, and that will give us this denominator here. Okay, so if we look at our center of rotation, looks like this. We've got 3.5 meters out here, and we have our seat out along here. We know that our seat is here. This is going to be 4.3 meters down along here. So if we just resolve these here, so we've got if this is 4.3 meters here, this is a right angle here. This is going to be, and remember this is alpha here, by the way. This is alpha. This distance along here is going to be 4.3 sine alpha. The distance up along here, by the way, it's going to be 4.3 cos alpha. So that's where they get the denominator here. You've got the distance from here to here is going to be 3.5 out to here plus 4.3 sine alpha. We can see, if we look at the forces up, they're going to be equal to the forces down. So what are the forces up then? Well, if we go back here, we can see that we've got this resolved force here, T cos alpha, acting upwards. That must be equal to mg. So we have T cos alpha is equal to mg. So that would just give us then the tension, then T is equal to mg over cos alpha. Okay, so let's look at the force to the left, if you like, in this case, it's the centripetal force. And that's just going to be the mass times omega squared times r. So our centripetal force then, our centripetal force is going to be equal to the mass times omega squared times the radius. Now we've just worked out the radius here. We've decided that it's going to be 3.5 out to here plus another 4.3 sine alpha. So that's where our denominator comes from. So it's going to be 3.5 plus 4.3 sine alpha. We know that our centripetal force then must be equal to T sine alpha. So T sine alpha must be equal to omega squared 3.5 plus 4.3 sine alpha. But we know from up here that T is equal to mg over cos alpha. So we can just substitute that in. So we've got mg over cos alpha sine alpha is equal to omega squared 3.5 plus 4.3 sine alpha. Now we have an m here on this side, so we can cancel that with this one here. So that'll give us, let's see, we have g times sine over cos is tan, so that's tan alpha is equal to omega squared 3.5 plus 4.3 sine alpha. Okay, so we're almost there. What I'm going to do now is just divide across by this bracket here and then square root both sides to give us omega here on the right hand side, and on the left hand side we'll have g tan alpha over 3.5 plus 4.3 sine alpha, and we just need to square root all that. I think that's what we were asked to derive. Let me just double check that. So g tan alpha over 3.5 plus 4.3 sine alpha is equal to omega. That's it. Okay, so next question then. Use dimensional analysis to show that the units for the expression square root g tan alpha over 3.5 plus 4.3 sine alpha are equivalent to the units for omega. Okay, so we have omega then is equal to square root g tan alpha over 3.5 plus 4.3 sine alpha. Now if we look at the left hand side here, the omega here is just radians per second. And on the right hand side then we've got the square root of g is going to be, that's going to be meters per second squared. Tan alpha, that's just a constant, so we can ignore that. 3.5 is a distance, and that's in meters. And then we have 4.3 sine alpha. Sine alpha is just a constant, so 4.3 sine alpha is just a constant. We can ignore that as well. Okay, now on the left-hand side here, we got radians per second. Now, if you think about it, a radian is just, if we have this angle here, radian is just going to be this distance here. This is part of a circle, that distance there, and let's say this is the radius. This is our angle here, theta. The angle in radians is just going to be the distance L divided by r, which is a distance as well. So really it's just meters divided by meters. So that will give us our angle here in radians. So meters divided by meters is just 1. So it's 1 over s on this side. On the right hand side we've got meters per second squared, so we've got meters per second squared over meters. That's just meters per meters second squared. So that meters will cancel with that if you like, and you'll get 1 over second squared. So it's the square root of 1 over s squared. So that'll give us 1 over s is equal to 1 over s. And that's it. We have we've used dimensional analysis to show that the units for that expression are equivalent to omega. So that's the left hand side and the right hand side are equal. So that's fine. Let's move on to the next one. Let's see. It is found by measurement that alpha is equal to 25 degrees. Calculate how many complete revolutions the ride makes in 1 minute. Okay, so we have, let's see, omega is equal to the square root of. Now we have G tan alpha, so it's going to be G tan 25 degrees over 3.5 plus 4.3 sine 25. Okay, so what you can do here is just do all of this on your calculator. You can find the tan of 25 multiplied by G, same down here, sine of 25 multiplied by 4.3 out of 3.5, and so on. You can do all of this on your calculator, and what you'll actually get is 0.927054835 and so on, and that's radians per second. So that's the angular speed of our seat. Now in a minute then, just multiply that by 60 and that'll give you 55.6232915 and so on, and that's radians per minute, because it asks us here to find how many complete revolutions the ride makes in 1 minute, so we've got to look at minutes here. One revolution we know is 2 pi, so one revolution is equivalent to 2 pi radians. So therefore what we've got to do is take our 55.623 and so on and divide that by 2 pi. So we're going to take 55.6232915. I'm going to divide that by 2 pi, and that will give us 8.8527 and so on. Okay, so our answer is going to be that it can do 8 complete revolutions. Hasn't quite reached the 9th revolution, so our answer is just 8 complete revolutions in one minute. Okay, so that's that one. Let's have a look at the next one, last part here. The person sitting in seat A throws a small orange into the air. The person imparts an upward velocity, vertical velocity component of 4 meters per second to the orange. Calculate the time from when the orange is thrown until it hits the ground. Okay, so basically what happens here is the orange is thrown upwards and then it comes down and hits the ground down here. So the distance down along here is going to be 6 meters. It's going to be 6 meters from here to here. This point here is going to be minus 6 meters from our start point. So this is 6 meters from here to here. We know that the velocity upwards is 4 meters per second. So that's going to be our initial velocity upwards. So let's see. We really only need to look at the j direction here. So let's write down what we have. We have the initial velocity u is equal to 4 meters per second. We have g is going to be equal to minus 9.8, well, minus 9.8, let's say in this case, per second squared. And we have the distance where it ends up then is going to be minus 6 meters from where we started. So we're looking at upwards, if you like, being the positive direction. Okay, so we're going to use s is equal to ut plus half at squared. So our distance is minus 6, our initial velocity is plus 4. We want to work out the time. It's going to be minus a half of 9.8, so that's minus 4.9, and it's t squared. So we have a quadratic trinomial here, so let's just bring everything over to one side. So that'll give us 4.9t squared minus 4t minus 6 equal to 0. So we've got to work out our time now. So let's see, we have a quadratic, so let's just put this into our minus b formula, our quadratic formula. So it's going to be t is going to be equal to minus b, so b is minus 4, so that's going to be 4, plus or minus the square root of b squared, so that's minus 4 squared, minus 4 times a, which is 4.9, times c, which is minus 6. All of that is over twice a, which is 4.9. Okay, so look, you can do all of that on your calculator. You do the positive version and the negative version here, but you get 2 times. So there's a time equal to 1.58760679 seconds. And you'll also get a time that's negative, it's minus 0.771 and so on. So we're not going to obviously count this one. This is our answer here. Now it doesn't say, I think, to give it to so many decimal places. Calculate the time when the orange is thrown, oh yeah, until it hits the ground. So it doesn't say to give it to any number of decimal places. I can never really understand why they don't do that, but that's as accurately as we can do it on the calculator anyway. So that's really it, and you ignore the negative version of our time here. Okay, so that's really it for this question.